All right. I think we'll get started. I'm happy to introduce Dr. Andy Norton, visiting from Virginia Tech. I count Andy not only as a teacher, but as a friend. Got to know him very well last spring. And I'm excited to hear what he has to share today. So, please welcome him.
Good, thanks for inviting me. And yeah, James was part of our graduate course at Tech last semester and really enhanced the experience for everybody. So I'm appreciative of that as well. So I'm Andy Norton, and I'm doing a shameless book pitch. This is a book that I recently completed. It'll come out in March. Rutledge is publishing it, but it is got a really long history going back to what drove me to graduate school to begin with. And that is, I have these philosophical questions about how it is that humans have access to something as powerful as mathematics that seems so much like truth that some people even think about it as the language of God. So how is it that we have that kind of power? What I learned when I met Les was that my philosophical questions might have psychological answers. And I came to see mathematics as a human construction, as a product of brain psychology, but very specific kinds of mental coordinations. And I'll talk about that more later. But yeah, so the fact that these philosophical questions have psychological answers mean that it's something we can actually research and we can actually learn from children, which is something that Piaget realized very early on. He was really interested in epistemology, but I think he might have preferred a time machine, but even if he had one, maybe the better approach was to study children's development, children's constructions, and some of the things that even Kant took for granted, like the construction of space, time, number, were things that you could actually see developing among children when they're first starting to structure their experiences. And then Les gave me the opportunity to see how to build these fine-grained models of the psychology of mathematics in middle schoolers. He'd been studying children from counting up through fractions, and that's where I found him, or he found me. And so I used fractions as sort of like a canonical example for fine-grained models of psychological development, but this talk is going to be much more broad about epistemology of mathematics much more broadly. So taking that one very honed in example and trying to see about what does it say about mathematics overall. And a lot of times it'll seem like what I'm talking about is just formal mathematics. But as you'll see in a quote that's going to motivate this talk, it's not about formal mathematics. That kind of gets it backwards. If you think about what I'm talking about as formal mathematics that we have to conceptualize, we're getting it backwards when really the formal mathematics comes from our own in-depth understanding of what we've been doing all along psychologically to construct mathematics. So I want to start with a very simple mental action. And this is one that a lot of childhood infant research with infants indicates might be even primitive. I mean, I'm always trying to be careful about claims of anything being primitive because it could just develop very early on. Anything being innate, right? Thought, time, space, number. He was wrong, we could dig deeper. So there might be something under this, but at least we know from studies that children as young as 4 months old can recognize vertical symmetries. They can recognize lines of reflection, and they prefer symmetric faces. And when they see this half lion's face, they can imagine the entire lion's face, tiger's face. So this is one simple mental action that we might be able to almost take for granted, but coordinating that mental action with similar mental actions is very productive. It's very creative in mathematics. So again, it might sound like I'm talking about something formal. So just to get this out of the way, a formal claim I can make is that every isometry of the plane is the composition of at most 3 reflections. Fine, that's something we can prove. But this is about a mental action of reflection and what happens when you take that personal power that you have of a mental action on reflection and composing it with other similar actions and what you can construct. It's your power. It's not something that we just prove in abstract algebra. There are 2 essential properties of these mental actions that give us this constructive power. Constructive and reliable. reliable in the sense that we think about mathematics as almost infallible. And what gives us this kind of power of mathematics is reversibility. This reflection, if I do it and do it again, I get back to where I started. So it's its own inverse. Every one linear reflection is its own inverse. Composable, I can imagine doing a line of reflection and doing another line of reflection, and I can wonder what that result will be. So reversible and composable mental actions, and this is just a really simple example, and that's what motivates the talk. Title, Reflecting on Reflections. So once you talk about reversibility and composability, you're at least 50%, maybe 2/3 of the way to a group. Because as soon as you say it's reversible, reversibility doesn't make sense unless you have some sort of place you can return to. And composability really doesn't make sense unless you're saying that you're reaching some kind of wholeness. You know, if every time you compose two things, you get something new, well, if you keep getting something new, keep including it, and eventually you get closure as well. So really, the only thing that reversibility and composability might not describe is this associativity condition of formal groups. But again, I'm not talking about abstract algebra here as something we're going to understand. I'm talking about reversible and composable mental actions. The fact that groups do appear late in the development and history of mathematics might be an indication that we're reflecting deeper and deeper on what's been riding underneath our mathematics all along, from complex numbers, and before that, integers, or before that, any kinds of geometric transformations of the plane. Things that we've been studying for millennia, we're realizing have a common structure to them, including the reversibility. And so Piaget has a really powerful way of framing this. I'm going to skip ahead. For it is only at the end of a sufficiently long series of reflective abstractions that the subject discovers the most profound characteristic of operations. Operations, he means reversible and composable mental actions. That they can be taken within structures that have laws of totality. This is why we had to wait for Galois to discover the group concept, which via Descartes, and we could go back even much further than that in the history of mathematics and see how these things were subconsciously used all along, not just algebra, geometry, early number systems. So his argument is turning the whole formalism on its head. This formal idea and this universal construct of group is a product, is us recognizing through reflective abstractions a product of our own psychology, and unrecognizing mathematics as a product of that psychology, not the other way around. So associativity is always the tricky one, but I kind of like the way that Piaget frames it. At least when we're talking about transformations or mental actions, associativity is kind of inherent. All it's really saying is that one transformation picks up where the other one left off. So if I have three transformations that take me from state 0 to state 1, and then from state 1 to state 2, and then from state 2 to state 3, as long as each transformation is picking up where the previous left off, then associativity is just independence of path. It's saying I could go this way, or I could take a shortcut, or I could take this shortcut, and I always end up in the same place. That's why like functions and any other kind of transformations, even in formal mathematics, are always associative. Not everything in mathematics is associative, but anything where you pick up where you left off. So Piaget framed this as independence of path, and you can see that sort of formalized here. I'm going to adopt the convention from right to left. So F followed by G followed by H. I can take this shortcut, think about that as a single transformation followed by H, or I could do F and think about that as a single transformation. And the result's the same. So there's a little history. This, I think you probably know this. So Les is my academic advisor. So this is Felix Klein. He's my academic great-great-great-grandfather. And so I'll tell you in a minute why that's important. Well, I'll tell you now. Yeah, Felix Klein, when he started his position at the University of Erlangen, Germany, introduced the Erlangen program. And the Erlangen program was trying to classify geometries. And what he was doing was he's saying, we could classify Euclidean geometry versus projective geometry versus non-Euclidean geometries, and even more abstract geometries, based on the groups of transformations that leave their objects invariant. So if we think about Euclidean geometry, what is it that'll leave a triangle invariant under transformation? And so isometries are, a translation or reflection or rotation. The triangle's internal relationships are unchanged. its relative sizes of its side lengths, its angles are all maintained under those transformations. So this group of isometries describes what Klein called the principal group for Euclidean geometry. And then in projective geometry, you get a bigger group, because any projection, it could turn a circle into an ellipse, but those things are equivalent objects in projective geometry. So the group is bigger. So you can see this group subgroup relationship, and he used it to classify geometries. But what really struck me about this program is that he's focused on transformations, not the figures themselves. He's almost defining geometric objects based on transformations, big coordinations of action, rather than three vertices located at particular points with particular coordinates, or three sides of particular lengths. It's about the transformations that define geometric objects, not static figures. So they kind of turn geometry on its head. Instead of focusing on figures, we can focus on the operations. He's doing it to classify geometries, but I think about this program more broadly to think about really revealing mathematics to be much more dynamic than it's often presented. And this is Emmy Noether. Emmy Noether arrived at the University of Erlangen soon after Felix Klein had left. She's no academic relation to me, not like Frank or Felix, but what Emmy Noether did was Felix Klein's program still had a big influence on Erlangen even after he left. And when Emmy Noether arrived, working without pay, by the way, because she was a woman, she eventually immigrated to the United States because she was Jewish. So and then to make things worse, she came to the United States and died of cancer not long after arriving at Bryn Mawr. That's the sad part. Happy part. She contributed greatly to algebraic invariance, which is the same kind of idea of Felix Klein's idea, but extended to algebra. She's saying, what kinds of transformations can we perform to algebraic objects, expressions, equations, roots of equations? What kind of transformations can we perform without affecting those things, without affecting the rates? What kind of transformation can we do to a polynomial without changing its roots? That's an algebraic invariant. And so she's already extending Felix Klein's program to thinking about algebra's dynamic being defined by transformations rather than just figurative expressions. So I mentioned like the early context for me to start thinking about these things, working with Les, was thinking about fractions. And this is an oversimplification, but two really important mental actions that students have to learn to coordinate to construct fractions as numbers are partitioning and iterating. Now, partitioning is not like reflecting. It's not something that we can claim to be innate. It's not something, you can imagine this, you might have experienced this if you try to teach students how to, you say, here's a whole candy bar, show me how to share this among 5 people. They've got 3 different goals they've got to coordinate at least. And that is, they need to create 5 parts. They need to make sure each part is the same size, and they have to make sure they exhaust the whole. And what you'll see in research on fractions is before students can really coordinate that and do this kind of partitioning, they will sometimes create 5 equal parts and have leftover, and they'll be like, go like, what's this? And like, oh, forget about that. Let's throw that away, right? So this mental action itself takes a coordination of even more basic, probably more sensory motor activity that the child is coordinating to construct this mental action. But once they have this mental action available, it becomes very powerful for them, especially when they can coordinate it with its inverse. So again, unlike reflecting, partitioning is not its own inverse. Iterating would be. So I can partition a whole into 5 equal parts, and then I can take any one of those parts and iterate it 5 times to reproduce the whole. So again, I have these reversible and composable mental actions. They're just a little more advanced than reflecting, and they're not their own inverse. But this pair of mental actions, as students learn to coordinate them, becomes very powerful in the construction of fractions.
No.
Okay. Right. So for example, they can construct fractions by creating a unit fraction of 1/5, iterating that 3 times, and construct 3/5 that way. So here's Jay Wilkins and I wrote a pair of papers about this development. So there's a lot more here than I can share, but they're called the splitting loop and the splitting group paper. But when you start coordinating these partitions and iterations, you start constructing a totality. Now that's not going to be a finite group, it's going to be infinite. So it's generative. When you're partitioning and you're iterating, you're generating new kinds of numbers. So I can think about, for example, 2/3 as partitioning a whole into 3 equal parts and iterating it twice. And then I can do more than that because, if I've constructed 2/3 as a coordination of these two mental actions, I should be able to take it with any other coordination and get something else in the group. So I can break that all the way down to mental actions, like 3/4 times 2/3. Again, I'm going from right to left. So I can think about that as iterating 3 times something that's partitioned into 4, and then the 2/3 iterating 2 times something that's partitioned into 3. And I'm coordinating these mental actions of partitioning and iterating to construct another fraction. Now, there's a couple of things in here that we're taking for granted. There's a commuting that's happening here, right? The associativity isn't so problematic. The associativity is all that's saying is every mental action has to pick up where the previous one left off. But what's more problematic is the commuting. And if you look at research, even in whole number, children can't take for granted that whole numbers commute. If you say 3 times 4 and 4 times 3, that can be an experimental problem for young children. They have to learn through coordinations of brain actions that those actually produce the same result, and then try to understand why that would always be the case. So there's a units coordinating issue already involved in this commuting. And there's an additional units coordinating issue that we talk about in the splitting group paper and the splitting loop paper with the associativity. So I'm not trying to discount the importance of that, but this is kind of a simplified model of how these two mental actions of partitioning and iterating can generate a group of objects for the student. They become constructive when they're coordinated with one another. But the coordination itself is very complex. So research, especially by Amy Hackenberg, indicates that students have to be able to coordinate 3 levels of units before they can really see where they can really think about fractions in general as an iteration of a unit that has its own relationship with the whole. So when you're talking about coordinating these mental actions, what's really challenging is coordinating the units that they produce. But once you do, it becomes really powerful because this group is isomorphic to the rational numbers under multiplication, the positive rational numbers under multiplication. So that's just one example. And I wanted to have a numerical example to complement what I'm mostly going to talk about, which is a geometric example. So going back to reflections, I might ask what happens when I compose a pair of reflections. And again, it's hard. These mental actions are mine. They're reversible and composable, so that gives me power, but it doesn't make it any easier. The work of actually thinking about what kind of transformation do I get when I take this mental action and compose it with this other mental action. So if I do a line of reflection about M, a reflection about line N, and a reflection about line N, if those 2 lines are parallel, you might try to reason through this, why that would produce a translation. So when I do a reflection over a line, I'm reproducing everything. It's that vertical symmetry or that symmetry. I'm reproducing everything on this side of the line over on this side of the line. So this distance is necessarily preserved. And I'm reproducing everything on this side of the line on that side of the line. So this distance is necessarily preserved. And what you can see is that the Hopi board changes orientation and changes back, but the end result is a translation that's twice the distance between the lines. You get D1 twice and you get D2 twice. But that's something I might rely on figurative material to try to work out and coordinate. But we got to stay focused on Felix Klein, Jean Piaget, Barbara Landauer, Emmy Noether. The transformations is where the mathematics is. So I'm trying to think I might use figurative material to keep track, but it's the coordination of these mental actions. That's the hard work of actually constructing mathematics. Here I've got an applet for this one. So the first applet that's on that website, you might play around with this and ask, what happens when you compose a reflection over line M and line N when they're not parallel? In other words, when they intersect. So suppose they intersect at point O. What happens when you compose those 2 reflections? And so I take an arbitrary point P. You can drag P to be further away from O if you want. You can drag P around the circle if you want. But what's going to happen is this triangle on the left side is going to be reproduced on the right side after that first reflection, giving me P prime. And it's going to be reproduced over on the other side of line M after the second reflection. And Every point on this line is preserved by the first reflection, and every point on this line is preserved by the second reflection. So only one point is going to be preserved in the composition. Only one point didn't move the entire time, and that's O. So I know I'm going to have a fixed point here, but I also know this length was reproduced on this side of the line, and this length is reproduced on this side of the line. So this radius of this circle is preserved. So I've got a fixed point, and P to P double prime is that same fixed distance. So it must be somewhere on the circle that is centered at O and has radius OP. And so what is the rotation? Well, by the angles being reproduced on the reflections, you can see this angle is that angle, and this white space angle is that white space angle. What you'll see is the rotation is twice the angle between the two lines. Okay, again, I'm pointing to figurative material, but I'm using the figurative material to try to trace the coordinations of the actual actions. So there's always a temptation, and this is why Felix Klein had to fight so hard with this program. There's always a temptation to take the mathematics as the figures, the triangles, the numerals you use to make your fraction, the part-whole relationship, the keep, change, flip. There's always a temptation to focus on the figures, but that's not where the mathematics is. The mathematics is in the coordination of your own mental action. When I'm trying to communicate to you, I've got a figure. But in my mind, I'm trying to do the actual coordination of the mental actions themselves, because that's what's generative. The figures are only a trace of that. So I have another app, because the question now arises, look, you just put together two reflections and you got a rotation. We've left the realm of reflections. Reflections don't form a group. We don't have closure. We haven't formed a totality. Now I've introduced rotation. So what happens when you propose two rotations? What if you do a rotation of 45 degrees clockwise about point A, and then you do a rotation 75 degrees clockwise about point B? Well, that first rotation, I know now is a composition of reflections. It's a composition of reflection over this angle bisector. You might see why in a second. I'm just going to say it for now. It's a reflection over this angle bisector to here, composed with a reflection over the line through AB to here. Because these two reflections, these two reflections, when composed, will form a rotation about their point of intersection. That's the point of intersection, twice their angle, twice the angle between them, which is this angle. So this composition of reflection 1, reflection 2, is that rotation about A of 45 degrees. So I've broken down this rotation to reflection, reflection. I can similarly break down this, and you can kind of feel it on the app. If you move the Hokey Bird face around, you can see how this is happening. But the second rotation, 75 degrees clockwise, is going to be reflection, reflection. So that's the rotation about B, twice this angle, which is 75 degrees. So I go reflection, 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 reflection. I've just composed 4 reflections, but the middle 2 were the same reflection. No, I don't know why it's not showing up. The middle 2 were the same reflection. So I went reflecting over this angle bisector, reflecting over the line through AB, but then I reflected over the line AB again for the second angle rotation, and those are their own inverse. So that just disappears. And all that's left is reflection over this angle bisector, followed by reflection over this angle bisector. And I know what that is. When I compose 2 reflections, I get a rotation about their point of intersection. That's the point of intersection, about twice their angle. So this has to be a rotation about that point, twice this angle. So again, and once again, I have to keep reminding that it sounds like I'm just talking about something you might learn in transformational geometry class, but it's the mental actions and it's not the figures, it's the coordinations, and all these coordinations are coordinations of your own mental actions. The only condition is those mental actions have to be reversible and composable. So once you've developed something like partitioning or iterating or reflecting or reversible and composable mental action, then all other mathematical construction is your own power to coordinate, which isn't easy. It doesn't make it easier, but it does make it yours. So we might extend this further. I got rotations, I got reflections, I got translations too, by the way. So those are 3 things I've generated just from composing reflections. I've generated all this stuff. Well, what happens if I compose a rotation and a translation? I'll consider that one. So in particular, if I do, in particular, if I do that, reflective over N and then L. So if I reflect over line N and then reflect over line L, then I should get a rotation about Q. And then we do a translation, reflecting over L, reflecting over M. They're parallel, so that should be a translation. So there should be a rotation followed by a translation. But as we just saw, if this is associative, these transformations have independence of path. If one picks up where the other one's left off, I can associate these two guys instead. And I know that I just get these two reflections, which I know is a rotation about point P. So I'm starting to get closure in my group. I'm generating things by coordinating my reflections in different ways, but I'm starting to get closure. I'm not getting new things after a while. And in fact, what I can show is that what I'm generating is the isometries of the plane, and every isometry of the plane is a composition of those three reflections. So if you want to see that kind of formally, take up your triangle. I'm trying to consider what kind of transformations leave this triangle invariant. This is the Erlangen program. This is Felix Klein's program. What transformations leave a triangle's internal relationships invariant? Well, I can move A anywhere around. That's a translation, which is two reflections. And then once I fix A, B has to stay the same distance from A because it's got to be invariant. So B has to be the same distance. So all I can do with B is make it a rotation about A, which is two more reflections. And then C, at that point, C, there has to be over here. So I might have to include a reflection, depending on whether I want C to appear on one side or the other. So 5 reflections. But as we just saw, the translation and the rotation can be reduced to 2 reflections. So those 5 reflections can be reduced to at most 3, depending on whether I have to reflect this C prime. But the only things that are going to leave this triangle invariant will be isometries, and I can see that I can construct those isometries by translation, followed by rotation, followed possibly by a reflection. And that's at most 3 reflections. So that's a nice formal theorem, but the generative aspect is just to see that I can construct these things at all, just by coordinating my own mental action of reflection. Here's just another example of the power we have when we don't focus so much on the figures, but we focus on the mental action. So if I can define this triangle as a kind of composition of rotations. I've got these 3 angular rotations that are bound within a closed figure, ABC. But I don't care about the figure. All I care about are the rotations. So if I look about my rotation about A, and this is in the app if you want to look at it. You go to the app, I'll actually show this. This one's much better than the other. So if I do that rotation about A, that line on the bottom is just helping me keep track. I don't care about the line. I don't care about the vertices. All I care about are these rotations and how they're going to be composed upon. So if I do that first rotation, it takes that bottom side to the left side. And now if I take that side and rotate it through B, it takes it to the right side. And now if I take that side and rotate it down by C, it takes it back to the original side. I'm at the same line that I started with, but upside down. I have rotated 180 degrees. I don't need to draw a parallel line through point C and talk about alternate interior angles. I can focus on my own mental actions of composing. If I define the triangle not as a static figure, but as a composition of these 3 rotations composed within this closed figure, and the closed figures just help me keep track of them, then I can see, of course, the sum of the angles in a triangle is always going to be 180. It's always going to be a half turn. I just saw the half turn. So that's the kind of power I'm talking about. Just to extend it a little bit more. Here's you can keep going with this. It's a little harder when you deal with bigger polygons because you have to keep track of how many times it flipped over. It'll be some multiple of 180. When I go bam, bam, I know it's going to come back to this line eventually. It's just trying to keep track of how many 180s I do. So you kind of have to keep track of every time you cross through this line. How many? So I crossed through it. Did I cross through it yet? Let me see. I go up here. I don't think I've crossed through it. I go through here. I don't think I've crossed through it. But now I've crossed through it twice. So I've done two 180s already when I get to here. And then I'm going to do one more 180. So it's going to be three 180s that I did for this pentagon. But you can generalize the same idea. I'm thinking about this pentagon as a composition of rotations organized within this closed figure, and they necessarily have to add the 540 degrees. Here's another one. This is going to get me into like a more advanced theorem, and I'm not going to go into too much depth, but there's two really interesting two-chords theorems. And there's an applet for this too. There's an app for that. If you go to that second to last one, I want to know something about. The angles in this picture. And I mean, P could be at any point inside the circle. What can I say about the angles that are formed by these two chords? So two chords intersecting at P inside of a circle. Is there anything I can say about its angles? Yes, that's true. These guys do add up, and you can kind of see it would rotate 180 degrees, like it would flip completely over if I put two of these together. I mean, I know you can think about it figuratively, you're just looking at a line, but to make it operative, thinking about this dynamic, the figure is representing flipping this whole thing over. Check out these chords. Would it be easier if I put these chords on here? If I show the chords that go through the center of the circle, then I might think about this angle as being measured by this arc length. But these angles are the same. It's the same arc length. Well, I've got something a little bit different here. I don't have which arc length measures this angle. Is it this arc length in blue? Or is it this one that's supposed to be the same that's measured in green? Which one is the right angle? They can't, I mean, if these are the same angle, it can't be the blue arc length and the green arc length. But if I think about the transformation from where I am to O, I'm not changing the angles. I'm only changing the frame. And when I change the frame, notice that everything that is added to the blue is taken away from the green. Or another, it might be easier to see that this amount right here, even just by symmetry, it's going to be the same amount right there. So the blue is going to increase by this amount, and the green is going to just decrease by that amount until they average out to the same thing. Well, if they average out to their angle measure, they always average out to their angle measure. The average of this arc and this arc will always be that angle. So it's like there's nothing special about this point except it's inside of a circle and where the two chords intersect, but I know its angle measure. Like I can measure this angle just by knowing that arc length and that arc length and averaging it, which is pretty powerful. And then there's a second two chords theorem that immediately follows, and that is so here you can see an average out. But it's the same average over here. But if I show these extra line segments, you'll also realize that we actually get two similar triangles. And that means that A times B will be equal to C times D. So you get a proportion like immediately. And the thing I'm trying to emphasize here is if I just focused on the figure as drawn, there's not much to say here. But when I think about the transformation and what is left invariant in that transformation, when I move P to O, what stays the same, what changes? When I'm thinking about the invariance and the transformation, the reversible mental action that I'm performing to do that, I get these really powerful relationships. So I'm just going to spend a little minute and then make sure we have time for questions. But there's a kind of notorious theorem that's related to this. It's called Pascal's Theorem. In fact, sometimes called Pascal's mystic hexagon. Oh, I forgot this. The inscribed angles theorem immediately follows. Because if the measure of this angle right here is the average of this arc and this arc, as I move that point to the circumference, one of the angles disappears. So I'm averaging this arc with 0. So this angle at P will be half of the angle at O. So that immediately follows. And then as a specific case, Bailey's theorem that this is a right angle. We usually prove that figuratively by saying these are radii of the same circle. And so you get isosceles triangles with base angles congruent. You set up this thing and you prove that x plus y equals 90. But you can see that this arc length right here is 180 at O. This arc length that goes flip around is 180. So that's half of 180, so it's 90. So you get like a lot of things come immediately. A lot of things that take a lot of formal steps in proving follow immediately when you focus on the transformations rather than the static figures. So I'm just trying to show the potential power, not just in learning mathematics, but in constructing mathematics, once you start focusing on your own mental actions and coordinating those mental actions. And again, it might not make it always make it easier, but it does make it yours. And that's what's important. That the mathematical power isn't Western mathematics. It isn't Pearson. It isn't, we proved that from last year.
Andrew
It's not
Wiles.
Andrew Wiles. You know, the mathematical power is coming from your own coordination of your own mental actions, which we should all have access to. It's just the effort of coordinating our own mental action. So that's why that's there. But there's Pascal's mystic hexagon is a really cool theorem. It's it says that whenever you have a hexagon, and this is sort of like a crazy case where you have a concave hexagon, 1, 2, 3, 4, 5, 6 sides. If you look at its opposite sides, where they intersect, this is side 1, so its opposite side is 2, 3, 4. Where they intersect, the 3 pairs will intersect on the same line. The 3 pairs of intersections will be collinear. And if you've ever seen proofs of this, it's a really convoluted proof, but I wanted to investigate this in terms of transformations instead of like how it's normally proved. And so start from a really simple case. Start from thinking about this angle being defined by half this arc length. And if I had a third point over here in the middle of that arc anywhere, so E could be anywhere between A and C, and I draw in this, well, I get, of course, this angle and this angle add up to this angle, right? So what I'm going to do is I'm just going to transform this vertex over this direction, and then transform, they're all collapsed on each other right now, but one of these vertices is the one that's defined by this arc, is the one that is subtended by this arc. The other angle vertex that I'm talking about is subtending this arc. I'm going to drag one of them over here and drag one of them over there. So they all look the same there, but when I drag them, you can see I'm still subtending this blue arc. I'm still subtending this pink arc, but now I've created the hexagon. And what I want to do is I want to say, I can think about this line segment as subtending that angle, but unlike arcs, subtending segments are fickle. Things can go wrong. What's going to happen is when I drag this vertex over here, this segment is going to get transformed. This segment is going to get transformed into how did it do that? Where did it go? Did it totally die? I thought I dragged it to okay. Yeah, that first segment is going to get transformed into this segment, and that second segment is going to get transformed into this segment. And then the claim that I make is that if I can set up proportions to calculate this length based on this length, and to set up this length based on this length, and then I can scale it back until it's back on that original line segment. And even though the original segment, the blue segment's length has changed, and the green segment's length has changed, their sum has remained the same. And so that's what I need to prove that that they're going to intersect on that same line. Okay, so I glossed over a lot of things, but I wrote this up for a CMJ article because I want to convince not just math educators, but mathematicians that there's a real power to thinking about mathematics in terms of transformations. So yeah, as much as I had to gloss over this one, the published proofs are a lot more complicated and rely on a lot more. They provide projective geometry for one thing. So I'm trying to come up with something that's like a much more intuitive transformational the transformations themselves, you've seen them all. They're really simple. The only thing I haven't like really argued here is why these proportions, when I take their sum, is the same as the original R2 length. But I want to stop there anyway. I wasn't really counting.
We'll spend the next 15 minutes in Q&A, or for however long we'd like to. So anybody who has questions for Andy. Thank you, by the way, Andy. It's wonderful.
Yeah, thank you. I apologize for the hecticness. But I was like, should I go here or should I not? I'm moving fast, which is maybe worse than doing it.
It was wonderful.
But most of what I talked about, not that last example, most of what I talked about comes out of chapter 2 of this book, which is coming out in March. And if you have any questions about it, anything related, you can email me. And if you want to see more details on that Pascal's Hexagon, I have that too.
Andy, I guess I have more of a comment than a question. I think that, you know, the Common Core standards do rely on a transformational understanding for things like congruence and similarity, and but I don't think that is well done at all in practice. I don't see teachers focusing on that. Can you think of any way that?
Well, like, so that's what I was trying to be careful about throughout is, yeah, some of this is just transformational geometry.
Mm-hmm.
But the argument I'm making is it's much more pervasive than that. First of all, it's not just about geometry.
Right.
And I mean, Hooper taught us that. But also I tried to share the fractions example to say this, you know, this is pervasive across mathematics. When we talk about coordinating our own reversible and composable mental actions, why are we restricting that just to geometry at all? But I don't even think it's pervasive in geometry. We spend a lot of time in geometry just talking about properties of figures rather than the operations that define the mathematical object. So even Felix Klein, who was a research mathematician, really hasn't been taken that seriously. I mean, his program had made a little ripple in mathematics, and it obviously affected people in his, you know, right after in the wake, like Noether. But it didn't have like a transformation about what mathematics is. And that's kind of what I'm interested in. I mean, I'm interested in epistemology of mathematics. And yes, I'm interested in it for its implications for teaching and learning. But I'm equally interested in it for its implication for what is mathematics. And if it's an epistemology of mathematics, then it should inform how we do mathematics, not just how we teach it and how we learn. And what excites me about it is how it can be personally empowering. I mean, I said it a couple of times now. It doesn't make the mathematics easier, but it does make it yours because what you're coordinating are your own mental actions. And so I don't know that I've seen this example. I mean, I wouldn't be surprised if it exists somewhere, but I don't know that I've seen this example of proving that a triangle is. And I could formalize it if you wanted me to. I could say, I'm looking at these rotations and I'm quotienting out the normal subgroup of translations and dilations. I don't care how this side length changed. I don't care that the point of rotation has changed. That's in group theory, I could take that as a quotient. I'm going to divide out translations and dilations and only focus on the rotations. And I could formalize this, but that's not my point. My point is I'm focusing on my own mental actions and coordinating them in a particular way. The fact that it can be formalized isn't what I'm relying on. In fact, it's quite the opposite. It's what Piaget said. The fact that it can be formalized is saying something about the roots of mathematics. The fact that when we get to where we finally form group theory and we discover that it's these same reversible and composable mental actions that Piaget has been seeing in children's construction of number is not a coincidence. And we've got it wrong if we say children are relying on abstract algebra to do number. They're not. Abstract algebra was relying on what children were doing to do number. It's us becoming aware of our own psychological ways of operating all along. So it really is mathematics as a product of psychology. And so that's the careful, I mean, I know this room is more sympathetic, but I gave a similar talk at Texas State and it was mostly mathematicians. And it's really hard to say, hey, I'm not talking about transformational geometry. I mean, none of that mathematics would surprise them. It's just flipping the whole thing on its head to think about it as, no, this started with children. It started the kind of mental action that children are basically born with, reflection, the kind of mental action we see them develop, especially through Les's work, developing partitioning and coordinating that with our iterating. And the fact that that coordination requires us to coordinate 3 levels of units, that tells us how hard that coordination is, because we know that it takes a long time for children to learn to coordinate 3 levels of units. But that's the kind of coordination that is generative of mathematics, not generative of how I understand mathematics as already out there. That's where the mathematics came from day one. We just didn't realize it until day 1862, or whatever it was. Year 1862.
Have you thought about the complex numbers?
Yeah, a lot. But so so there's a chapter in the book that gets into complex numbers too, and the kind of geometry of number that appears and the generalization of number. I mean, it starts with like what Katie was writing with directed quantity. Complex numbers are really nothing more than a generalization of the idea that we can think about numbers as not just magnitudes, but having direction as well. And when you have integers, you got 2 directions, and there's a reversibility built into that as well, which is why we have integers under addition forming a group again. But the complex numbers do something else, and they do it so beautifully that it combines addition and multiplication in a sort of whole, in this completeness that Piaget was talking about. So you can see it everywhere. And I always have to apologize to Les because, you know, he builds these fine-grained models of how children do this. We are learning from students where mathematics is coming from. And anytime I talk about transformational geometry, or much even more so if I talk about complex analysis, I'm jumping ahead. But I'm doing that because I'm trying to show the same thing that we're seeing with number is pervasive in all of mathematics. I'm not going to have the same fine-grained models of how we're constructing it, but you can see the same idea of reversible and composite momental actions, the efforts that go into coordinate them, and the generative power they have, whether we're talking about complex analysis, geometry, algebraic topology. I've thought about all these things. I'm thinking about number theory now. And so it's just pervasive.
What do you teach it? You know, aspect the teachers, are you going to teach mathematics? About what might they be teaching? I mean, I think I'm very interested in how do you think about that?
Well, I think it's a really hard problem because you know how long it takes to try to build these really fine grained models of students' mathematics. And now we're saying, okay, teachers have to teach all these different topics. Are they really going to understand units coordinations and fraction schemes at the level that, you know, it took us years to, and you see in your graduate courses how hard that is to teach in itself. But there's some level, and I think maybe it's just this more of a meta level to thinking about building on students' mathematical power. I mean, I do see value in building fine-grained models, but they're never going to get to that same fine-grained level that graduate students spend years getting to. You know, for one topic, and teachers have to teach all these topics. But if they did understand in general that you try to identify what mental action students have available. You think about ways to leverage them. Drew and I were talking about this before. You think about the manipulatives or technology you're using with them. What affordances do those technologies or manipulatives give the students to coordinate mental actions in new ways? Like when they're manipulating a cube or a freeze pattern. Like, what are the mental actions that those manipulatives are affording so that they are coordinating mental actions in new ways? So for me, the most powerful thing is just that meta. And then the question is, how far do we go into the models in every particular domain? What's realistic? People who are doing this and having success include Vial and Ron Zerg. The 2 projects that they're working with pre-service, with in-service and pre-service mathematics teachers, trying to see how they can build models of their students' mathematics. But how fine-grained can we expect them to get when they're expected to cover all of this mathematics that's coming out of the textbook, and they're trying to transform it all into models?
Yeah, it seems like you had said from the beginning of this talk that there's something productive there, just a paradigm shift that would be moving from like perceiving it as conceptualizing formal mathematics to conceptualizing the operations that generate.
Yeah,
mathematics.
it's turning
Just
all
that
on its head.
paradigm itself is productive.
And then you start taking your students seriously. They're not learning about something that you're teaching them. They're constructing mathematics based on what they are. And so you as a teacher have to understand, what are they bringing to the table? What kinds of sensory motor activity did they need to engage in because they haven't internalized this activity? What have they internalized but haven't coordinated in new ways? What technologies and manipulatives allow them to start coordinating in new ways? It's not about the figures. But the figurative material, including especially manipulatives, because it can be manipulated, give them opportunities to do new things. Give them opportunities to go through this complex coordination. And that's where the complexity is. I mean, the individual mental actions like partitioning can take a long time to develop. But then even when you have those, trying to coordinate them with one another adds whole other level of complexity. As indicated by the mathematics that you generate. You know, the coordination has to be at least as complex as the mathematics that you're building from it. I'm at that meta level. Like, and I always feel like I apologize less because fractions did give me an angle. But I'm interested in thinking about it as being transformational math, and not even just about teaching and learning, but about mathematics itself, even for research mathematicians. Like, my pipe dream is to think about how this might be productive in informing research in mathematics. If mathematicians focus more on identifying the mental actions that are defining mathematical objects and how they might be coordinated, could that be a productive line of doing mathematics, even for research mathematicians? Yeah.
I know you and I got to talk about these things before, but I'm intrigued to ask why groups? Because it seems to be the key or even the reality that is undergirding this psychology. It's the foundation, it's the ground that we're walking on, even Piaget. That is why we had to wait for Galois to discover. He doesn't even say construct.
Yeah, I don't know what the translation is. But
Yeah, but like the language is, and the language and the way that groups are treated is very that this is the core of things, and why groups and not.
So I can
anything
answer
else.
the question why reversible and why composable. But before I answer that, why reversible and why composable? Those two things, like I was saying, get you like 2/3 of the way to the group. But the splitting loop paper that I was talking about is not associative. It's not associative because when students first start coordinating, partitioning, and iterating, they aren't keeping track of all the units involved. They're not. They just know that when I partition a partition, I get a partition. When I partition something into some number of parts and iterate that same number of parts, I'll get back to where I started. They have that coordination, that's splitting. They have that. But until they can coordinate the 3 levels of units, there's only a qualitative distinction being made by partitioning and partitioning to get a partition, iterating an iteration to get an iteration. And because it's qualitative, if you can actually show this mathematically, PPI will not be the same as if I put P and I together first, or if I put the P and P together, I get PI, which is just the identity. If I put the P and I together first, I get identity and then P, so I get P. So I get P, which is not equal I, depending on how I associate those 3 mental actions. So splitting loop is not associative. So you don't always get a group. The reason Piaget argued that the group was like the whole thing is because that's where you get the completeness. That's where it all comes together. When I can coordinate all those 3 levels of units, I get all the different kinds of partitionings. I can make distinctions between them. I can construct every kind of fraction. So the group brings completeness. But before there's completeness, you do have reversibility and composability are the essential things. So why those 2 things? Reversibility gives me complete reliability. Reversibility is the sense in which it's something I have in mathematics that I don't have in science. I have never had a perfectly reliable scientific experiment. There's no way of repeating a scientific experiment exactly the same. But in mathematics, I run it forward and backwards in my head a million times, and I know it's going to be the same. It's ridiculous. I don't even do it because I know partition the continuous whole into 5 parts. I iterate that part by it. I'm right back. It's completely reliable. I can return it at the same state because what I'm operating on is not something empirical. I'm operating on my own mental actions, and I'm just coordinating them. So that's the importance of reversibility. The importance of composability is I don't get anything without composability. I don't generate anything. So the only way mathematics can be generative is if you have these reversible mental actions that you can combine them. So it's not necessarily groups. It's reversibility and composability. But when that thing becomes complete, that's when you have a group. So that's why Piaget would always say, children operating at the lower stages, and I'm not as strict on the stages of development, but he talks about a sensory motor stage and a concrete operational stage at which children don't really have totalities. They're able to compose things and reverse things kind of in activity, but they're not operating with a totality where they take for granted ahead of time, they anticipate what's going to happen. So it's only at the formal operational states that he talks about groups. So that's a little more harsh than I would say, but that's a distinction he makes, even that it's not always about groups. He does see groups as like the end all, yeah.
I'm just wondering if you thought about how this coordinates, maybe we got Thompson, some of Thompson's people here, Pat Thompson. I wonder how this coordinates with Thompson's inputs upon quantity and physical quantity and physics. How do you articulate that?
I've done a little bit of work on this only because my graduate student who has Kevin on that thing, is looking at quantitative reasoning around and covariational reasoning and its relationship to units coordination. So to me, I put primacy on units coordination. For Pat and his students, I'm sure they put emphasis on quantity, but the connection is you can't measure anything until you have a unit. So you can't measure anything until you have a unit. And so there's a connection there. It's just which one you focus on, the primacy of it. So I can't say much more, but it's something I'm very interested in, and that's why Sarah is actually doing her dissertation this May. My graduate student will finish in spring or May, spring or summer. She's kind of helping me get closer connected with Kevin's work and Pat's work and Marilyn's work by studying this.
You got anything to say?
That's why I'm on Sarah's project to let her do it. No, I think like, right, so like a little bit of practicality too, in terms of thinking like who Pat's worked with, and I've worked with, especially college level students. Like there's an assumption we make, which is a problematic assumption, that we assume at least an activity they can coordinate 3 levels, right? Because they're college students that are primarily secondary mathematics majors. Again, that's a problematic assumption, but it's an assumption taken because we're focusing on other things. We're focusing on their coordination of magnitudes of the plane and how they produce a trace from that. We're focused on those things. Where I do think that there's the question of, I think this is what ties into Andy's work in terms of his reference to figurative material. The question is, for me, in terms of units coordination, to what extent is it dependent on the figurative material that's there, and what is the quantity being conceived? Take the fraction bar, Andy, you go to that. Just go to the image of the fraction bar. Okay. What, like, to a student, my question is, what is being partitioned? Is it a length or is it an area? Or does it not matter? Right? Like that to me is like the question I would ask there from the quantity perspective. What is being partitioned? And does that matter in terms of operations? I think that's what you're getting at. Like, if you take now your perspective on that, well, we get to this meta level where we realize we can engage in these quantitative operations, and regardless if it's an area or a length, they're equivalent. The operations we're enacting are mathematically the structure to them. There's equivalence to those, or invariance, maybe is the right word. Right? That in terms of I can partition an area, I can partition a length, I can iterate an area, I can iterate a length.
I know. Have you included the concept of the interiorization versus internalization, and thinking about the interiorization of the figurative material, stripping the material of all the sensory material, all of that.